Hello everybody, in today's video we're going to be going over how to find absolute maximum and minimum values in a closed interval. So if you haven't seen the previous videos, I recommend watching them because I show you exactly how and the exact steps to find your critical points, because we're going to need to do that in order to find our max and min values. And just as a brief recap, when we have a function, let's just make a random graph, it doesn't matter. Let's say we have this function right here, right? Okay, so just by looking at it, we can identify the maximum. This is our max, right? This is our maximum, absolute maximum. This is our, right here, it's included when it's colored in. We have a closed interval from A to B, right? So this can be included, and this is our absolute minimum. This guy is our local max, and this guy is our local min. So the point of finding the absolute maximum and minimum values in the closed interval is that sometimes you're going to find that your endpoints can be your absolute max and min, and in this case of this function, our absolute minimum is one of our endpoints. So we need to make sure that when we are finding our max and min values, we are including our given endpoints, because sometimes the max and mins can lie within them. So I hope this makes sense in just about a few minutes when we get started on this one. So what's the first step? Well, it's finding the derivative. We're going to find our critical values. And to do that, like I said in the last video, we must first find the derivative of our function. The derivative of this function is 3x squared minus 6x. Then we must equal our derivative equal to 0, and then pull out the greatest common factor. Here, the greatest common factor is going to be 3x. And when we do that, we're left with 3x times x minus 2. Then we're going to set both of these equal to 0. And when we divide this 3 out, we just get x equals 0. Remember, as long as you get a whole number under 0, it's still valid. But the minute you get 0 in the denominator, it's undefined. Then over here, let's add this 2 so that we get x by itself. So our two critical points are 0 and 2. Does it fit in the interval? Yes, it does. Our two critical points does fit in the interval, because again, these are inclusive. So the 0 passes. All right, after we've done that, the next step is going to be evaluating our critical points and our endpoints, which are these guys, into f of x. So what does that even mean? It means we are basically just going to plug them in. So let's do that. Let's do that in a different color. Let's do it in orange. So we're going to plug it into our original function, not the derivative, right? So let's do our critical points first. Let's do 0. So we're going to have our original function, right? Good. And this is just going to equal 1. Right off the bat, we can tell. It's just going to be 1 for that one. And then our next guy, let's do 2. So we're just plugging 2 in to our original function. And here we're going to get -3. And then let's keep going because we're running out of space a little bit. So let me write it over here. So then we need to plug in our endpoints. And because we already did a 0, we're not going to do the 0 again because it's just going to give us the same value. So what's the point of doing extra work? So let's do that. Three minus 3 times 3 to the second power plus 1. And this gives us 1. So what are absolute and minimum values? Well, let's take a look. What's our lowest value? Our lowest value here is -3, and our highest value is 1. So if you are given an assignment through like Cengage and they're asking you what's your absolute max and absolute minimum, that's what they want you to put in. So for absolute minimum, you would get a box and you would just type in -3. And then for this guy, there'd be an absolute max and then there'd be a box and you just type in 1. All right. So again, this is our min and this is our maxes. We actually have 2 maxes. So if you're given like paper homework, right, we could write it as absolute max equals 1 at x equals 0 and x equals 3, right? Because that's how we found these. It's like plugging in those x values. And then for absolute min, we could write that is equal to 3 at x equals 2, right? Because that's how we found it over here. All right, so this is basically all we're doing over and over again. It's pretty easy. So feel free to pause the video and try it out. So let's jump into this guy. First step is to find our derivative. The derivative for this is going to be 18x to the second power minus 18x to the first power minus 216. Next, we are going to pull out our greatest common factor, will also equal to 0. Then pull out our greatest common factor, which is going to be 18. And when we do that, we are going to be left with 18 times x squared minus x minus 12. Then we're going to factor this out. And what we need to do is we need to list our factors for 12. So we have 1 times 12, we have 2 times 6, we have 3 times 4, and that's really all we have, right? So we need to look at which pair, when added or subtracted, gives us this value, which is a -1. Well, this guy right here is going to do that. If we have a -4 plus 3, we're going to get -1, which is exactly what we want. So this is going to work perfectly. So let's plug that in. We're going to get x minus 4 times x plus 3. Then we're going to set these two equal to 0. We're not going to set the 18 equal to 0 because it's not going to give us x value, so we don't care about that guy. All right, now let's just solve like normal. We're going to get x by itself. X equals 4, -3, -3, x equals -3. So these are critical values. So let's see if it falls within our interval. And would you look at that? They do. So that means we can proceed with evaluating them. So now we're going to plug in our endpoints and our critical points, because remember, like earlier when I drew that function and plotted the max and mins and local maxes and mins, your endpoints can sometimes have an absolute max or min. So that's how we're evaluating it. Okay, so let's plug these guys in into our original function, right? So let's start off with 4. Let's do our critical points first, then our endpoints. So let's do this guy. So 6 times 4 to the third power minus 9 times 4 to the second power minus 216 times 4 plus 1. This is going to give us -623. Now we're going to plug in -3. 6 times -3 to the third power minus 9 times -3 to the second power minus 216 times -3 plus 1. Okay, that was like exhaustive. That's going to give us 406. And now let's do our endpoints. So we didn't get lucky where we had the same number and we didn't have to do all 4. So now we have to do all 4. All right, let's do this. 6 times -4 to the third power minus 9 times negative 4 to the second power minus 216 times negative 4 plus 1. This is going to give us 337. All right, last one. We have 5. So 6 times 5 to the third power, minus 9 times 5 to the second power minus 216 times 5 plus 1. Okay. We get negative 554. So if you plug it into the calculator exactly as you see it, it's going to spit out these numbers. So I'm not going to do like all of the work for this, because chances are if you're in Calculus 1, they're probably going to let you use a basic calculator at the very least, right? So from looking at this, we need to look at our lowest and highest values. So our lowest value is negative 623, and our maximum value is going to be 406. So in this case, our absolute max and minimum do not lie within our endpoints, but we had to check anyways, right? So we can write that, again, if you're doing it for WebAssign, they're going to ask for absolute max. You're going to put 406. They're going to ask for absolute min. You're just going to type negative 623. And then if you have it on paper or another form of homework, whatever, you're going to write absolute max equals 406 at x equals negative 3. Absolute min equals negative 623 at x equals 4. So that is our answer. Okay, these are really easy. This one's going to be a little different. So I do have a natural log in here, and then I do have the quotient rule, and then I have a trig function. So we have some good examples, but you'll really see it's just repetition. It's just the same thing over and over again. So I'm not doing a lot of examples, unlike the critical points where it really does involve a lot of practicing to really get used to it. So our first step, find the derivative. So this is just going to be u prime over u. So 2x over x squared plus 1. And then, hello? Oh, here it is, right in front of my face. Okay. So, sorry. I usually keep a sheet next to me to make sure that I am on the right track. So, let's keep going. We have f prime of x equals 2x over x squared plus 1. So, we do not take the bottom and equal it to 0. We only take the numerator and equal it to 0, because if we were to take all of it and equal to 0, then the whole derivative would just be undefined, right? Because the denominator would be equal to 0. So we only take the numerator and equal it to 0. So let's take her and equal her to 0. And when we divide, we get x equals just 0. Now that we have our critical point, let's see if it lies within our interval. And we can see that it does perfectly, actually. So we're going to plug in our critical point and our endpoints to see where our absolute max and minimum is for this function. Let's do that now. Let's do our critical point first. Remember, we're plugging it into our original function, so just as it's shown, we must plug it in. Then we get ln of 1, and ln of 1 is 0. Then let's do our endpoints, ln negative 2 squared. There we go, plus 1. Probably should use brackets, but it's whatever. Okay, so what do we get here? ln, and the negative 2 squared is going to give you a positive, right? we get 4 plus 1, f of -2 equals ln of 5. And this is going to give you a decimal when you plug it in. It's going to be like 1 point something, something, something. And so let's do our last one. And it's going to give us the same thing, right? Let's see. ln here, I'll do brackets. I'll be proper. We have 2 squared plus 1. This is just going to give us 4 plus 1. We're going to get ln of 5. So our absolute maximum is these guys. So we actually have 2 absolute maximums, and we have 1 minimum, because 0 is smaller than like 1 point something, something, something. And if you plug ln of 5 into your calculator, it'll spit out the exact decimal. And then, I don't know, maybe your professor will have you, or teacher have you like round it. I'm just gonna write ln of 5. I'm not gonna go into the decimals. So our absolute maximum, max, is ln 5. Absolute min is 0. And then if we want to write it the long way, we can say absolute max equals, all right, Siri, calm down, equals ln of 5 at x equals -2 and x equals 2. Our absolute min equals 0 at x equals 0. So these are our answers, right? See, it's pretty easy. It's not bad at all. All right, this one we're going to use our quotient rule to find our derivative. So let's do this. Again, feel free to pause the video. I feel like it's really easy. Let's see. So we have to do g of x times f prime of x minus g prime of x times f of x all over g of x squared, where g of x is our denominator and f of x is our numerator. So let's solve that now. Let's do our pink. So we get x squared plus 1 times the derivative of the numerator, which is just going to be 1, right? Minus the derivative of our denominator, which is 2x, times our numerator, which is just x, all over x squared plus 1 squared. Let's condense this before we equal her to 0. We're going to get x squared plus 1 minus 2x squared. Then we have x squared plus 1 squared, right? And then we can actually simplify this, right? Because we have her and we have her. So let's simplify these guys. Just because there's a parenthesis doesn't mean anything, because there's nothing in front of it or behind it to be multiplied. So we can actually drop these parentheses now. So when we drop these parentheses, we can combine our like terms in the numerator, and then we can set our equal to 0 and figure it all out, right? So let's do this now. We get f prime of x equals x squared minus 2x squared is going to give you negative x squared, right? Because it's a positive 1 in front of the x squared. We just don't write it. It's implied. All over x squared plus 1 squared. Again, we're only going to set the numerator equal to 0, because if we did both, then the whole thing becomes undefined, and that's no good. So we get 1 minus x squared equals 0. Let's move the 1 over. We get negative x squared equals -1. Then we divide by -1, because again, there is a 1 here. And the only reason why we're dividing it by 1, well, -1, is because of the negative value. We don't want a negative value alongside our x. When we divide, -1 over -1 gives you a +1. So we are left with x squared equals +1. Then to get rid of our squared, we must use our square root because there's a tiny 2 here, and we don't write it all the time because it is implied. Anytime it's greater than 2 or less than 2, it's usually straight out written, so you understand. So this will cross out this 2. Then we have x equals the square root of 1. And what is the square root of 1? Well, it's plus or minus 1, right? So x equals plus or minus 1. So this is our critical values. We have a positive 1 and a negative 1. So does it fit within our interval? Yes, it does. So now we can plug in both our critical points and our endpoints into our original function to see where our max and min is. So to give us some room, I'm going to clean this up because this actually took a lot more space than I had anticipated. Oh, okay. All right. Okay, so that's our critical point, right? So now we're going to plug them in. All right, when we plug it in, we get f of, let's do our negative 2. Let's do something different. Let's do our endpoints first. Negative 2. Okay, we get negative 2 over negative 2 squared plus 1. That's going to spit out negative 2 over 4 plus 5, 4 plus 1. So f of negative 2 gives you negative 2 over 5. Let's do the next one in a different color. Actually, no, we'll stay with the same color. All right, let's do f of 2. We're plugging into the original function. So 2 squared plus 1. Okay, we're going to get the same thing we got for this guy, right? It's the same exact thing. So we get, oh, no, it's not. That's right, the negative 2 at the top. So instead of a negative 2, we get positive 2 over 5. There we go. And now let's plug in our critical points. So f prime of negative 1 equals negative 1 over negative 1 squared plus 1. This is going to give us negative 1 over 2, because negative 1 to the second power is going to give you a positive 1. 1 plus 1 is 2, right? Now let's do our positive 1 equals 1 over 1 squared plus 1. And now we're going to get 1 over 2, but a positive 1, right? So let's take a look-sees and see where our max and mins are. We see that this is going to be our absolute minimum, and this is going to be our absolute maximum. So in this case, our absolute max and mins are not in our endpoints. They're actually our critical points. So we can write this as absolute max equals 1 over 2 at x equals 1, and then absolute min equals negative 1 over 2 at x equals negative 1. So those are our answers. Okay, last one. Yay. Let's take a look here. So I actually did this problem in the last video. So if you remember it, or if you watched it, the critical point part is going to be pretty easy. All right, let's take our derivative. That's our first step. And we get the derivative of sine x is cosine x. The derivative of cosine x is negative sine of x. We're going to set this equal to 0. And then I'm going to move sine x to the other side, because now we're able to pull out values. So where does, on the unit circle, And between our interval, we have to pay attention to our interval from 0 to pi over 2. From 0 to pi over 2 on the unit circle, when does sine of x equal cosine of x? And if we look, we find that the only place between those 2 points is going to be x equals pi over 4. So that is the only place, and if you want to look at a unit circle, it's going to be pretty obvious, right? Or maybe you just knew it off the top of your head. So that's the only place between 0 and pi over 2 where we have sine equals cosine. So let's keep going. We know it lies in the interval, so we're not going to have to check that, right? So now we just have to plug it in. We're going to plug in our 3 values into our original function. So let's do our critical point first. Sine of pi over 4 plus cosine of pi over 4. So sine pi over 4 is just the square root of 2 over 2 plus, and then cosine of pi over 4 is the square root of 2 over 2. When we simplify this, we can get, again, the denominators are the same, so we can just go into it. So we have a 1 in front and we have a 1 in front here. We just don't write it. So when we combine this, we get a 2 square root 2 over 2. Then we can simplify these 2's because 2 over 2 just gives you 1. So then we get just the square root of 2. So when we plug in our x value, pi over 4, we get the square root of 2. Okay, let's keep going. Let me just move it a little bit. Okay, cool. Now let's do our endpoints. F of 0 equals sine of 0 plus cosine of 0. Okay, off the top of your head, I pray you already know what this is. So we just get 0 plus 1, and then 1. So f of 0 equals 1. Then our last one is going to be pi over 2, sine of pi over 2 plus cosine of pi over 2. Okay, sine of pi over 2, 1 plus 0. And then we just get f of pi over 2 equals 1. All right, so let's see where our max values are. Our absolute maximum value is going to be this guy. Because when you plug that into a calculator, it's going to spit out a decimal. It's going to be like 1.4 something, something, something. And that's obviously greater than just 1. So, therefore, this is our max, and these two are our mins. And we can write that. Absolute max equals square root of 2, or you can write the decimal, at pi, well, at x equals pi over 4. X equals pi over 4. Right? Then we can write over here, absolute minimum value is 1 at x equals 0, and, wow, that is awful, and x equals pi over 2. So that is all for this video. In the next video, I'm going to be showing how to find local mins and maxes in an open interval. So if that's interesting to you, stay tuned for that next video.